India traveled 4,000 miles in just 30 million years. Very fast in geological time.
India was drifting northwards across the Indian Ocean at very rapid plate tectonic speeds. And we're talking here between 10 and 12 inches per year, which is very rapid.
It's this speed that goes some way to explain the unique size of the Himalayas. Like a giant train wreck, India collided with Asia. The land and ocean floor that lay between literally folded up under the enormous pressure. But folds are only part of the story. Alone, they don't explain the Himalayas' vast size. Rocks can only be bent so far. Once rock has been bent beyond its limits, it breaks and causes a fault. The process of faulting puts different rock types one on top of the other. The rock was pushed so far beneath the Earth's surface that it reached heat in excess of 4,000 degrees Fahrenheit and began to melt. 20 million years ago, this amazing conveyor belt system was at work. As India pushed northwards, a liquid band of buoyant rock was forced towards the surface and cooled, forming a solid layer of granite.
Southern part of the Tibetan Plateau to form the high peaks of the Himalayas. And it's this conveyor belt system that keeps the high Himalayas actively uplifting to this day.
The mountains were repeatedly jacked up to epic proportions. It's this unique process which accounts for the Himalayas' immense size.
This is a view of the Pacific as seen from space. A vast expanse of water that covers almost a third of the Earth's surface. Today, only 1% of this vast ocean is land, and much of it owes its existence to the explosive powers of volcanoes like Kavachi. 1,500 miles north of the equator, perhaps the most famous group of volcanic islands in the world, Hawaii. Still one of the most volcanically active areas on Earth. And this is Kilauea. Like all volcanoes, it's plumbed into the very heart of the Earth, home to a lot of hot, angry rock. Rising from 60 miles below the ocean's floor, this lava has flowed non-stop for 25 years. On the lower slopes, the lava travels at less than 100 meters an hour, betraying little of its awesome power. Nothing can survive this smoldering blanket.
Beneath the ocean floor is a mysterious area of super hot liquid rock. Hot enough to melt a hole through the Pacific plate, punching up fresh lava. It's called a hot spot. The ocean floor is creeping gradually northwest at 3 inches a year, but the hot spot under it doesn't move. A volcanic island builds up, but as it moves away from the hot spot, it is cut off from the source of lava and dies. Over the hot spot, a new volcano forms.
The thickness or viscosity of lavas can be shown in a number of ways. Hawaii lavas are quite runny. Honey is a perfect example of that. If you have the volcano putting out Hawaii-like lava, it's going to run quite easily down the rock. Whereas if you have something more like these blocky lavas, they're going to be a little bit more like peanut butter. They'll still run, but the viscosity is much greater.
The viscosity of lava is primarily determined by the amount of silica it contains. Silica is the most abundant mineral in the Earth's crust.
We're going to take a closer look at volcanoes. A volcano is a vent in the Earth's crust where molten rock, gas, and steam erupt onto the planet's surface. The molten rock beneath the Earth's surface is called magma. Lava refers to the magma ejected from a volcano. Magma's mineral composition determines how its lava behaves. Mafic magma contains high concentrations of iron-rich minerals and magnesium. Mafic magma flows freely, producing lava capable of traveling some distance before cooling and solidifying. Felsic lava contains silica and produces thicker lava. Thick lava can't travel as far. Because felsic lava solidifies quickly, it produces the classic cone-like volcanoes, which are called composite volcanoes. Felsic magma can also solidify beneath the Earth's surface, creating magma chambers where hot gases and magma build up. This causes composite volcanoes to explode violently. Mafic lava produces a broad, low-profile volcano called a shield volcano. Instead of explosive eruptions, shield volcano eruptions cause lava to flow in all directions. Mauna Loa, a shield volcano on the Big Island of Hawaii, is the world's largest volcano, rising 13,680 feet above sea level. Seismologists classify volcanoes as active, dormant, and extinct. Active volcanoes are either erupting or likely to erupt in the future. Dormant volcanoes have not erupted in recent history. Extinct volcanoes have exhibited no activity for long periods and are unlikely to erupt in the future. And that's the hot news on volcanoes.
It began around 4 billion years ago. This is Rotorua in the North Island of New Zealand. It's one of the most volcanically active places on the planet. This is a landscape where you can travel back in time. Rotorua is similar to how the early Earth would have looked.
In its early days, the planet looked very different. Just like here, the ground was hot with perpetual volcanic activity. Nasty chemicals brought up from below stained the land. And noxious gases bubbled up from steaming pools.
Molten rock usually lies hundreds of kilometers underground, but here, as in Ethiopia, it's much closer. Yet the effect is very different. Sulphurous fumes and bubbling hot pools hint at the power that is just beneath the surface.
Volcanoes can be deadly. They also provide benefits. Volcanoes created 80% of the Earth's surface, as well as much of the air we breathe today. Volcanoes create rich soil for farming, and many countries harness their subsurface heat to create geothermal energy. Both creators and destroyers, volcanoes prove that beneath its calm surface, Earth remains a living planet, and a restless one.